Can't move that without something happening that I don't want. Dang it. All right. Okay. All right, so we're going to cover a couple sections today. The first one is not the most important thing in the world, okay? So, and we talked a little bit about Poisson's equation before, and so this one is called the method of images. So I forgot what section that is. I want to say 3.2, 3.2. Yeah. So, all right. So we went over some ways to calculate E, right, by using Poisson's equation, et cetera. But this is kind of just a little bit different. And it's not, I gotta say, the most useful thing in the world. So we're not going to spend a huge amount of time on it. Okay. But it's called the method of images. Okay. All right, so we're going to set up the classic image problem. Problem, there we go. Okay, so you have a point charge. You have a point charge Q. And it's held a distance above an infinite grounded conducting plane. So we have a infinite plane, so this is infinite. Grounded conducting plane. Okay, and its distance above the plane is d. Okay. And we want to know what is the potential in the region above the plane. So the question is, what is potential in region above plane? Okay, and we know that it can't just be, so if the plane wasn't there, right, that would be simple. It would be just KQ over omega, right? Just the regular potential for a point charge would be super easy. However, Q induces some kind of charge on the plane, and we don't know how much and where it's distributed, really, right? We know it's probably more near the charge and less somewhere, we don't know. Okay, but we do have the uniqueness theorem that tells us that if we can figure out what the V is on the boundaries, then we are halfway there, right? Okay, so we know what the boundary conditions are because we know that the plane is grounded, yeah? So we know that V has to be 0 on the plane. Let's make a coordinate system, we might as well, right? So we'll make a little coordinate system here where this is Z, and so Z equals 0 on the plane, right? And XY will be in and out of the, to the side and into the board and out of the board, right? Because it's a plane. Got it? All right. We know that the boundary conditions are that V equals 0 when Z equals 0. Because the plane is grounded, right? Okay, and we know that probably if we go really far away from the point charge, right? So if we're like the distance from the point charge, because remember the plane's infinite, so we're going out and we go far away from the point charge, we know that V is also going to go to 0, right? Okay, so we know that V is going to be going to 0 when for the distance x squared plus y squared plus z squared a lot greater than d squared, right? It's another way of saying you're just far away, yeah? Okay, so here's what the method of images does. You kind of forget about the real problem and you think about 2 point charges, one that's Q, your regular Q, whatever you have. This, we're just saying we have a plus Q up here. And then you have a negative Q underneath the plane the same distance away. It's like an image charge. It's not real, Okay. Okay, because remember, if we can write down something that satisfies the boundary conditions, that is the answer. If we can write down a potential that satisfies the boundary conditions, that's the answer. Okay, so this is like a cheat. Can we make this other problem up to give us an idea of how to write down something and see if it gives us the boundary conditions? Do you see what I'm saying? Because once we know, if we have an equation for V, that when V is 0 when Z is 0, and V goes to 0 as this distance gets big, we're done. That is V. Who cares if there's an imaginary image charge that doesn't exist? Yeah? Okay, so that's the idea. All right, so we're going to pretend there's another charge. So just to draw that out just a little bit, so just pretend this is the plane. We have Q up here, and then we have a minus Q down here, right? And they're both the distance D, except for this one's positive D and this one's negative D, right? So this is Z equals D, and this is Z equals negative D, right? Okay, so we can write down the potential for that. We pretend there's no plane. There's no plane. Sorry, I forgot to mention that. I should say that, right? There's no plane. So this thing here doesn't exist. I'm just drawing it there for you. Does not exist. Well, then the problem just becomes really easy, right? Because we know it's KQ over omega for both of these situations, right? And then we can add them because of superposition for potentials. Okay. So we can write down the answer is V of X, Y, and Z. So we know it's going to be a function of all those is K. So 1 over 4 pi epsilon naught. And then for the first charge, it's Q over, where the distance away from Q, which is going to be X square root of X squared plus Y squared plus Z minus D squared, right? Yeah. Okay. And then for the negative charge, it's Q over X squared plus Y squared plus Z plus D. Uh-oh, hold on. Get that away. Plus D squared. I'm just using distance formula back from, high school. That's why it's minus D for the positive charge and plus D for the outcome. All right. All right. Well, that's a candidate. Now we've got to figure it. Does that satisfy the boundary conditions? Well, let's see. The first one, when Z equals 0, take a look at it. Tell me, do you get V equals 0? When Z equals 0. Yeah. Okay. Check. Check on the first one. Okay. The next one we just got to think a little bit about, right? So when X squared plus Y squared plus Z squared is a lot greater than D squared, what do we get? It still goes to 0. Therefore, that's the solution, but only for Z greater than 0, right? Yeah, because we didn't say anything about less. So this is it. That's the answer. Okay. So the method of images is just a way to cheat your way into getting a potential that satisfies your boundary conditions. So when you get your boundary conditions satisfied, you're just done because of uniqueness, which is great property of this equation. Yeah, does that make sense? Okay. All right. So that's really all I'm going to say about that. I mean, there are other situations where you can do this, but we're not going to go through them. Okay. Yeah. It's just kind of a nice application of uniqueness theorem, I feel like. Yeah. Okay. All right. Let's move on. Okay. This is 3.3. And this is now really delving into solving Poisson's equation or Laplace's equation using separation of variables. Now, in general, your differential equations class here, does anyone remember if they do partial differential equations at all?
Yeah.
Yes,
I mean, I feel like I need to see it and I could pretty easily confirm. Like,
see a partial differential equation?
no, like, well, yeah, we did partially.
Like the process.
Yeah, like the process.
Yeah.
Okay, so the way that we do this is, and you've seen it in quantum before too, okay? The first thing you always should try is separable solutions in partial differential equations. You may not be able to find a separable solution, it may not work. Matter of fact, in quantum mechanics, if your potential energy function has time in it, you can't separate. You just can't. And so you're screwed. Right? You have to use perturbation theory to approximate an answer, or you have to use a computer. Okay. But you should always try, see if you can separate your equations. Okay. All right. So let's do yeah. Let's see. Hold on a second. I want to see which ones I want to do. Yeah. Okay. Let's do a Cartesian coordinates example. We will go to spherical because that's way more useful in general. Okay. All right. So Cartesian coordinates example. All right. So let's have two infinite grounded metal plates. So obviously conductors. And let's let them lie parallel to each other. And parallel to the XZ plane. Okay. We'll have one at y equals 0 and the other at y equals a. Okay. All right. Now at x equals 0, right, we have an infinite strip. So we'll get a better visual on this in a second, which is insulated from the plates. Right. And maintained at a specific B0 as a function of y. Okay. We want to find V between two plates. Okay, that's what we're after. Okay, so let's look at, see if we can figure out how this geometry works. All right, so I'm going to draw the y-axis up, the x-axis out. And then the z-axis is going to come in and out of the board, right? Kind of like this, but drawn askew, obviously. Okay, so that means that the planes, and I'm just going to kind of draw because at x equals 0, right? There's a strip. So what does that mean? So think about it this way. I'm gonna have a very hard time drawing this. I'm very sorry, but I will try. So we're gonna have kind of the strip. . That's our strip, right? And that just keeps going. Yeah. And then we have the planes. So one of them is here at x equal, sorry, at y equals 0. And it's infinite, so, but I can't really draw, obviously, so I'm gonna try to draw like this. Okay, there's the bottom plate. Okay. Now, obviously, it extends this way, extends into this part here, but I'm not drawing that part. Right? Does that make sense? Okay, and then on top is the other plate. See if I can draw that in pink, maybe. So on top is the other plate. Yeah, it's just awful, but I don't know what to tell you. There's the bottom one. And then the top one. Pretty bad. My bad. Okay, this is gonna be A, right? So there's a pink plate on A on the top and a blue plate on the bottom. The worst picture known to mankind. Sorry, don't know what to tell you. Kind of sucks. Okay. All right. Maybe writing the boundary conditions will help. So let's write down the boundary conditions. We kind of know a bunch of stuff. So we're gonna have boundary condition 1 is that we know that they're grounded, right? So that V equals 0 at Y equals 0. That's the blue plate at the bottom, right? Actually, why don't I make that a blue? That'd be better. V equals 0 at Y equals 0. Grounded bottom plate. Okay, and then we have for the pink plate on the top, we have V equals 0 at Y equal A, grounded top plate, right? Okay, we have for the yellow strip, we have V equal V0 of Y on the strip, and that's when X equals 0, right? Strip. Okay, and then when we go away from the hot strip, because everything else is 0, right? Everything else has V equals 0. We go away from the hot strip, right? Hot meaning like, you know, like it's plugged in, right? Then it should be 0. So that'll also put in yellow. The potential should be 0. We're far away. So V should go to 0 as X goes to infinity, right? Because we're far from the strip. My computer starts doing its thing. It can't run Zoom. Well, let's check the how much. Oh no, we are in trouble, you guys. We have 14%. It's doing its thing where it's like running, means it's not gonna charge. Maybe, but I think it's Zoom that's eating the power. What is it called? Activity monitor. Windows server. I have no idea what that is. I don't know if I should kill that. What do you think? I don't think Windows server is a good idea to kill. Probably not. All right. Doesn't look like anything else is really eating anything. I don't know what that is.
Why do you have Windows server?
No, it's not Windows. It's window. No, it's like Windows Server, right? It's like, I bet you it's the thing that controls all the, windows that that are open. Core audio. What the hell is that? I don't know, maybe that's something to do with Zoom recording. See, it is just useless because I can't turn anything off. Okay, never mind. So see what happens. Your new computer. Okay. All right, so again, if B is specified on the boundaries, so it's unique and determined, right? Okay, so we can write down Laplace's equation. And I want you to notice that the configuration is independent of Z, right? Doesn't matter what Z we're at. Right, of course, in the picture, I didn't draw everything going on the Z, on the negative Z axis there, but it goes all the way down. So I don't need, the Laplace's equation in Z, I don't care, right? Also, I don't have any charge. Right? So it's Laplace's equation, not Poisson's equation. Okay. All right. Actually, let me copy this layer because I'm gonna need those boundary conditions. I want to keep them. All right, let's turn you off and I'm getting a new computer in July, but it's way too dang far away. I didn't take it to the Apple store because I called IT and they were just like, the only thing that can be done is because it doesn't have any, it's old enough, it doesn't have like, oh, replace it for free or anything like that. So is that they can wipe it and see if it helps and come in, right? But I don't have time to do that until after school's out. So I just decided to get a new computer in July when the fiscal year rolls around. Huh? You need a new one? Yeah, I'm getting a new. I know, I went to the Apple store just to figure out which one I'm buying. So I'm gonna buy an Air this time because they've caught up with how powerful this is. The Airs are just as powerful and they're lighter. Yeah. Okay, and cheap. Okay, we're gonna do Laplace's equation in 2 dimensions in X and Y. So we're gonna have do this in our blue, I guess. Well, I'll do it great. So we have partial squared V, partial X squared plus partial squared V, partial Y squared equals 0. Because it's independent of Z, we don't care about Z. Okay. We don't expect V to have a Z in it, right? Okay. All right. So now we're going to look at separation of variables. So what that means is we're going to look for a solution V of X and Y that is the form capital X, that's a function only of X, and capital Y, that's only a function of Y. So this is a multiplication of 2 functions, right? So it might be like capital X is like X squared plus 2, and Y, capital Y is, Y. So this would be X squared plus 2 times Y, right? This solution, but separable, which is different from having like X squared Y plus 2, plus 3Y squared. That's not separable into 2 multiplying functions, right? Okay. All right, so we'll try this. So actually, I do like to color code when I do this because it helps to keep track of everything. So I'll make this guy an orange guy. All right, there we go. All right, so now the first thing we do is we substitute into that equation. That's always the step, right? Okay, so we're going to substitute in. So we have d squared dx squared, and then we're going to substitute in our x and our y. Oh, I should have chosen 2 different colors. So let me do that. Y of y. Okay. And y. Okay. And so this is taking the derivative of both of those plus d squared dy squared, and we have the x and the y, right? And this is equal to 0. Okay, so the great thing here is, of course, on this term, the y can just come right out because it doesn't depend on x. And on this term, the x can come out. So this gives me on this side, we get, a full, sorry, my bad. We get y times the full derivative, right? Ordinary derivative. And now I can write this all in orange, my bad. So d squared x dx squared. Notice I changed it to a full derivative because x only depends on x, okay? And then plus x can come out. And then this becomes a full derivative in blue of the y function. Yeah. Okay. I really don't want to erase those boundary conditions, but okay, I'm not going to do that. So what I'm going to do, the next step, always same thing as always, is that you divide through by this quantity, right? By these two together. You divide the entire equation because you have 0 here and you can do that, right? So we just divide through. Over here, we're going to have x, y, and over here, we're going to have x, y as well. Yeah. Okay, notice that this cancels out here. And this cancels out here. And we get two equations, right? So I want to erase this side now. Sorry, don't get two equations, my bad. Two terms. So you get 1 over x in orange. We have an orange side, 1 over x, d squared x, big X, d little x squared, plus we get in blue 1 over y, d squared y, d little y squared, right? Okay. And that's equal to 0. Well, obviously, if they're equal to 0, right, then one of them has to be the opposite of the other, right? Because think about it, this is the crux of separation, is when you change a little x by a little bit, this term changes, but this term does not, right? And so if you change little y by something, this term changes, but this term does not, right? That means they both have to be equal to a constant, and one constant has to be the negative of the other, so they add to 0. Okay. So so we like to set those to particular constants. It's kind of a when you have a second order differential equation, it's kind of tradition to let this one be equal to like k squared. The squared is because we're going to be taking a second derivative. But doesn't make any difference to the solution. It's just kind of nicer. And then in blue, we let this be minus k squared, right? And that would add to 0 and you're good. But they have to be constants because there's no way that if one is varying with x, that x, if one side changes, the other side would have to change by the exact same amount or opposite, right? By negative of that amount. All right, so this gives us two equations now. Okay, we have two equations. We have d squared, oops, sorry, orange. D squared capital X dx squared equals k squared capital X. I just brought the capital X up, if you don't mind. And then on the blue, and I am rushing through this a tiny bit because you guys said you've seen this before, and I know you've seen it in quantum. Yeah. So there's our two equations, easily solved equations, by the way, solved equations that all of you should be experts because we've solved them in quantum, like that same equation a billion times in quantum, both of those things. And it's a trivial example of a homogeneous equation, linear, ordinary differential equation. Okay, but let's go through it. We're going to solve each of them, and I'm going to have to erase. Maybe we can come back to the boundary conditions because this is annoying me. So, because I'm not really giving myself enough room for anything. All right, so we'll erase all this, but I have it in another layer. All right, let's solve. Okay, so I'm going to rearrange this a little bit. And write this equal k, my bad, equal k squared x, and over here, d squared y, dy squared is equal to minus k squared y. Okay, so we'll solve them now. Okay, anytime you see homogeneous linear differential equation, you use an exponential, right? I mean, notice what the form is. It's a function where you take the second derivative and you get back the function. Exponentials are perfect for that. Sines and cosines as well, as we know. Okay. All right. So I'm just going to let x equal e to the lambda x. I don't know what lambda is yet, right? If I take the second derivative of this, I get lambda squared e to the lambda x, right? So this gives me lambda squared e to the lambda x is equal to k squared e to the lambda x. And those come out, and lambda is equal to plus or minus k. This is the reason we have used k squared instead of just some random constant c, right? Because then we don't have to carry around a square root. Okay, all right, fine. So this means that x is equal to some constant times e to the kx and plus b e to the minus kx, okay? Now notice that k is real. There's nothing, right? We started with a k squared and we took the square root. It's not imaginary. Those are dying and growing exponentials for x. Okay. All right. We'll apply boundary conditions when we're done. Getting everything. Okay, for the y function. All right. Again, y, that y equal e to the lambda x, a different lambda. I'll use gamma x. Then we get gamma squared e to the gamma x is equal to minus k squared e to the gamma x. Those cross out, we get gamma squared is equal to minus k squared. Therefore, gamma is equal to plus or minus I k. So now we do have imaginary solutions, okay? Which means that the solutions for y are sines and cosines. Yeah, but I think I will write it in terms of sines and cosines at some point. Yeah, so I'll do that right away. So I know I'm skipping around here, but I'm expecting you guys to understand this because you've had this a few times. Okay, so I could write it as e to the plus ikx plus, you know, some other constant times e to the minus ikx, but I'm also free to write it in terms of sines and cosines if I want. And I actually prefer sines and cosines for boundary conditions. So I'm going to write y is equal to some constant c sine of ky. I kept saying x in the last thing, sorry. Plus d cosine of ky. Okay. All right, we have our solutions. And now we're going to implement boundary conditions. Okay, the first boundary condition that I'm going to implement, I'm going to go back and show you the boundary conditions. Okay, is this last one actually, because it says as x goes to infinity, b has to go to 0, right? And I know my solution for the big X is the only function of X I have. And it's easy to implement this because I'll show you, right? So let's go and implement boundary condition 3 on this. So for boundary condition 3, or 4. Okay, we know that V has to go to 0 as X goes to infinity. What does that tell me about the solution for big X? What happens now if you put in big X? What happens if you put X equal infinity in there? Okay, is that what we want? So what do we do? Remember, boundary conditions are so you can solve for A, B, C, and D.
Set it equal to 0,
Set what equal to 0?
big X.
No.
No.
Yep. So this becomes B e to the minus kx because A has to be 0. So you just solve for 1. Yeah? Okay, so now we've done that. That's nice. Okay, well that's an easy one. Okay. And now let's write down our solution as a whole before we move on. Okay. So I'm gonna write that down. Well, hold on. Okay, so yeah, let me just move this. And I'm gonna write it as a whole now, because notice that here, right? So now in V, so V of X and Y is now e to the minus kx times C sine, oops, I want to write the color coding still, sorry. C sine of ky plus D cosine of ky. All right, and I absorbed that B constant into C and D, why not, right? Doesn't matter. All right, fine. Now we're on, now we have to move on to the next boundary conditions. Okay. Let's see, boundary condition 1, let's go back, I think. No. Boundary condition 1, B equals 0, Y equals 0. Let's do that one. Okay. Let me see. All right, so boundary condition 1, which was, I forgot what the color was, but I don't care, all right. So 1, it's V equals 0 when Y equals 0 because the plate's grounded, right? Okay, so let's set Y equals 0. So we have 0 must equal e to the minus kx, and I'm going to stop the color coding for a second, right? And then C times the sine of 0, right? Yeah? Yes? And sine of 0 is 1. No, sine of 0 is 0, my bad. And then D cosine of 0, which is 1. Right, so we get e to the minus kx d, right? E to the minus kx just cancels out. We don't care about him. But this tells us that d equals 0. Right? Rewrite this solution one more time now. V of x, y equals e to the minus kx, and then c sine of ky. Okay, excellent. All right, let's erase this. The next one was V equals 0 at Y equals A for the next plate, for the top plate, right? I'm gonna check the time for me, would you? 11 what? All right, probably gonna have to be a video at the end. Yeah, my guess is there's a video. All right. Okay, maybe not, but I think there is. Okay. Fine. So let's do boundary condition 2. V equals 0 at Y equals A. Okay, so now let's put that into our function. we have 0 is equal to e to the minus kx times c times sine of ka. Okay, well, that's easy too, because whenever we have so think about k, right? So if k is equal to n pi over a, right, where n is 1, 2, 3, dot, 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 we'll be good, right? Because so when, because then we would have sine of n pi y over a. Yeah? That makes sense? So when y is a, it'll just be sine of n pi, which is 0, always, right? Okay, so that's cool. So that means we actually do have the whole solution. The only thing we haven't implemented is well, we'll see. Let's just write it down. So v of x and y now is e to the minus k x, and then we have c still, right? And then we have sine of n pi y over a. Right. Yep, there's our solution so far. Okay. The only one we haven't implemented is boundary condition 3, which is that weird one, which is about the strip, right? So we have boundary condition 3, which says v is equal to v naught of y at x equals 0. Okay, so we have to do this. This is a little weird, right? So think about x equals 0 in there. If you put x equals 0 in there, you're just going to get c times sine of n pi y over a. But what we've ignored here is actually this kind of equation has infinitely many solutions. Okay, so you can you really, as you can see, like the n can be 1, 2, 3, 4, right? There's many. So actually the general solution is a linear combination of all of the solutions. Right? Does that make sense? Yes or no? Yes. And Laplace's equation is linear, which means if you have two solutions, right, you can add them together, and you still, and that is a solution. And if you have three solutions, you can add all three together, and that will be a solution, right? So you can extend this to an infinite sum of solutions will still be a solution. Okay, well, why is that going to help us? You'll see. All right. Now we do need a new layer. All right, so actually the general solution to this is v of x and y is equal to the sum n equal 1 to infinity of cn. So now each n gets its own c, right? E to the, okay, why is there n back? Give me a second. Oh yeah, k. I forgot to tell you guys something, actually. So let's just go back for a minute, just for a second before we go to our linear combination. So we had this with e to the minus kx sine of n pi y over a, but we said that k was n pi over a, right? So we can actually put that in here, and there was a c here. So we can put that in for this k, e to the minus n pi x over a sine of n pi y over a, okay? All right, but then the general solution is this linear combination of all the different n's. Okay, sum n equal 1 to infinity of, each one has its own c, because there's no reason why it wouldn't, right? E to the minus n pi x over a sine of n pi y over a. Okay, now, this satisfies all of the boundary conditions except for 3. We don't know anything about 3 yet. Okay, so when we implement boundary condition 3, okay, which is that v equals v0 of y at, what was it again though? Yeah, at x equals 0, right? Yeah. That's what the strip is. Yes? Okay, so, we have a condition that says at x equals 0, so v of 0 y must be, v0 as, that is a function of y. We don't know what that function is, by the way, it's just something, some random thing we don't know yet. And then, this must now be equal to this sum, n equal 1 to infinity, Cn, but x is 0, so this just, that e becomes 1, and then you just get sine of n pi y over a. Okay, so somehow. All right, well, it turns out that you can always find appropriate CNs such that this will be true. So if v0 of y is like y squared plus 2, you can find appropriate CN so that the sum over all those sine functions gives you the function y squared plus 2. That is a theorem of orthogonal functions. And in fact, the sines are orthogonal functions, just like we had in quantum mechanics. Those look exactly like the solutions to the infinite square well, right? So you can find CNs that'll work. Yeah, you might have to sum all the way to infinity. Yep. You might not. But there's a way to find them. And it's called Fourier's trick. We used it in quantum. Yeah. And so what you can do is you multiply both sides of the equation. So we have equation here and equation here. You multiply by, it's going to be Fourier's trick. We're finding this, the appropriate CNs, right? So sine of n prime pi y over a, and then you integrate. So let's multiply both sides. So I'm going to say on this side, I'm going to have the integral between 0 and a, right? That's the strip, right? And then we have v0. Oh, let me write this in a little bit more color coding. 0 to a. And then we have v0 of y, whatever that is, like y squared plus 2. Okay, unfortunately, I'm gonna have to stop the recording there. I might be able to save this if it stops the recording.